I'm going to do 3 screencasts. The first one is going to be on how circuits work. The second one will be a manual process for analyzing the circuits and determining the flow of current through each branch of the circuit and the voltage drop across each resistor. The third screencast will I'll teach you a matrix method for evaluating them. It's important that we know how to do the manual process and really truly understand what's happening. This is about understanding, not about getting the problem done. But the third method, the matrix method, will allow us to do the problems a lot more quickly once we understand what we're doing. All right, so how do circuits work? We might think about this as a power supply. Say it's a 12-volt power supply. We have 12 volts, and let me move that down a little bit. 12-volt power supply, and that's going to supply current to the circuit. And so the circuit will draw current from the power supply. We'll call this I1, and I1 is going to flow through the first resistor. And when it gets to this point, it's going to branch off into 2 parts. We'll call those I2 and I3. Okay, so it's like a fork in the river, kind of. The current splits into 2 paths. And I3 goes around the outside, goes through here, crosses that resistor, flows back down this path. And then at this point, it meets up with I2, which is flowing in this direction. And then the 2 of them combine at this point, at this junction here. So we have I2 and I3 combining. And since they both split off from I1 up at this point, the sum of I2 and I3 will be equal to I1. And then I1 then will flow back into the negative terminal of the power supply. And so I1 flows out and I1 flows in. And we have conservation of charge. Okay, so that's kind of how it works. One thing to point out is that the voltage is pretty much a constant. Okay, we can think about the power supply as providing a constant voltage. And depending on the circuit will draw more or less power. And so the thing that varies in the circuit would be the current. Okay, as we add more and more resistors, or as we would draw more or less power. Okay, and so we can change the number of resistors, we can change the value of the resistor, but that's actually making a physical change to the circuit. The thing that's going to vary is the current. Okay, now we could be more sophisticated, I suppose, and model the power supply as having an internal resistance, but we don't have to do that. We could do that if we need to. So for the most part, we would consider the power supply to be a constant. I mean, just think about it. If you look at the battery in your calculator, it says 1.5 volts on it, and that stays the same pretty much. All right, so we now kind of have an idea of how the circuit behaves, and the real question is, why does it behave the way it does? Okay, why does it do that? Why does current flow at all? And to answer that question, we need to kind of talk about, well, how are the charges distributed? And if we look at the power supply, we can see that we might have positive charges on this end and negative charges on the other end. Okay, and so the way the circuit works is the charges are distributed non-uniformly throughout the circuit. And it's this non-uniform distribution of charge that moves the electrons through the circuit by creating an electric field inside the wires. Okay, so let's take a look at how that's done. To simplify things, what I'm going to do is simply remove the negative charges from the bottom, and we'll just consider the negative charges to be 0. So we have 0 charge, just to simplify things at the negative post. And so let's just look at how the positive charges might align themselves. We have, what do we have, 12 on that side, and so we would have a non-uniform distribution. Let's say we have 6 or 7 on this side, and then across this element we might have, well, maybe it's going to be reduced, of course, And so let's have 4 or 5 here, and then maybe 3 down here, and this 3 then would apply to the entire wire. This is all one piece of the wire down here. And so we would have 3 charges down here. And so we can see then that there's a non-uniform distribution, and that creates the electric field inside the wires. Let's blow up one of the wires and kind of see what that might look like. We'll take a cross-section of a wire or maybe a circuit element, and we could see that we might have a positive charge buildup on one side, maybe a large charge distribution on one side and a smaller one on the other side. Okay. Now, this charge, of course, is distributed on the outside of the circuit elements or the outside of the wire because they kind of repel each other, and so they want to get as far away as they can. So you can think of them as being basically coated on the outside of the wire or the outside of the circuit element. But inside, they generate an electric field. And so there's an electric field inside the wires, and that electric field produces a current that flows through the system. Okay. Now, I could do a whole screencast on this very next thing I'm going to put up, but except the fact that the current is going to depend on the electric field. Okay, and it's going to be proportional to how big the cross-sectional area is, because that tells you how many electrons are in there. And it's going to be also proportional to how conductive the wire is, which is a physical property of the material that we're using to make up the circuit elements and the wires. And rather than use conductivity, we will use the inverse of conductivity, which is resistivity. And so we have an equation now that explains pretty much how current is generated by the electric field. I mean, after all, let's think about it. What causes electrons to flow in the first place? Well, we know the electrical force is equal to the charge times the electric field. And so the electric field is pushing electrons through the circuit. Okay? It's pushing them backwards through the circuit. I say backwards because Ben Franklin got it wrong. It actually flows, the electrons go from negative to positive, but we use the flow of conventional current to be from positive to negative. And so that's the use that we're going to apply in our analysis. Okay, so it's the electrical force then that pushes the charges through the circuit. All right, now let's take another look at the electric field. We also know that the electric field is the gradient of the voltage, the change in potential across the length of a circuit element. And so across the circuit element, we would have a potential difference. Okay, and that's what we've been calling voltage. And we could say, well, okay, that's across this differential distance, delta x. Applying that in our equation here, then we say, well, we have this relationship here where we have the potential over the length of the circuit element, and we can rewrite that in the following way. In terms of the potential, then, we can say the voltage across the circuit element is, let's see, proportional to the current times the resistivity times the length of the element, or the length of the wire segment, divided by the area. This term we commonly refer to as resistance. Okay, and so this brings us to Ohm's law, which we can write then as the potential is equal to the current times the resistance. This is going to form the basis of analyzing all of our circuits in the next 2 screencasts. I hope that this summary is useful. In our next segment, then we'll be starting to talk about how to apply this then to find the currents across the various circuit elements and to find the potential drop across each circuit element.